In 1964, NASA engineers were designing something remarkable. Not a flag-planting mission, not a brief sortie to collect rocks and leave footprints. They were planning permanent human habitation on the Moon, powered by compact nuclear reactors that would hum quietly in the lunar regolith, generating kilowatts of continuous power for years without refueling. The Lunar Exploration System for Apollo, known as LISA, represented the logical next step after the initial Apollo landings. While Kennedy's challenge focused the nation on reaching the Moon before the decade ended, NASA's long-range planners were already thinking beyond that first bootprint. They envisioned extended surface operations, mobile laboratories traversing hundreds of kilometers, and habitats that could sustain crews for months at a time. All of this required power, substantial and reliable power, far beyond what solar panels or fuel cells could provide in the harsh lunar environment. The numbers told the story. A basic Apollo lunar module carried enough battery and fuel cell capacity for perhaps 75 hours on the surface. The LISA concept called for 14-day missions initially, extending to 30 days and eventually 90-day stays. The power requirements scaled accordingly. Life support systems, environmental controls, scientific instruments, communication arrays, and the mobility systems needed to make extended exploration worthwhile. All of this demanded kilowatts, not watts. Solar panels presented problems. The lunar day lasts 14 Earth days, followed by 14 days of darkness at temperatures approaching -170 degrees Celsius. Battery storage for 2 weeks of night operations was impractical with 1960s technology. The mass alone would have required multiple Saturn V launches just to deliver the power system. Nuclear reactors offered an elegant solution. Compact, reliable, indifferent to day or night, capable of operating for years with no moving parts in the primary system. The Atomic Energy Commission had been developing space reactor technology since the late 1950s under the SNAP program, Systems for Nuclear Auxiliary Power. By 1964, several reactor designs existed that could theoretically meet NASA's requirements. SNAP-10A had already flown in space, the first and only U.S. nuclear reactor to operate in orbit, generating 500 watts for 43 days in 1965 before a non-nuclear system failure ended the mission. More powerful designs were on the drawing boards. The MOLAB concept emerged from this planning environment. The Mobile Lunar Laboratory was not a small rover like the later lunar roving vehicle that flew on Apollo 15, 16, and 17. MOLAB was a truck-sized pressurized vehicle, a habitat on wheels that could travel hundreds of kilometers from the landing site while maintaining shirt-sleeve environment for a crew of 2. The design studies showed a vehicle roughly 6 meters long, 3 meters wide, mounted on large wire mesh wheels that could navigate the boulder fields and crater slopes that defined much of the lunar terrain. Inside, the crew would have bunks, a small galley, waste management facilities, and a comprehensive suite of scientific instruments. The vehicle would serve as both transportation and temporary base, allowing geological surveys far beyond the range of a suited astronaut on foot. Power requirements for MOLAB were substantial. The life support system alone needed several kilowatts continuous. Heating during the lunar night, cooling during the day, communications, navigation, the science package. All of these systems drew power constantly. The mobility system, whether electric motors or some hybrid arrangement, demanded even more during transit. Early studies suggested a minimum of 10 kilowatts, with 15 to 20 kilowatts preferred for operational flexibility. No battery technology of the era could provide this for the planned mission durations. Solar panels would have worked during the lunar day but required the vehicle to remain stationary during the 2-week night or carry impossible amounts of battery storage. A small nuclear reactor, perhaps derived from SNAP-8 or similar design, seemed like the only viable option. The base habitat designs went further. LISA planning documents from 1964 and 1965 describe modular structures that could be landed separately and assembled on the surface. These weren't the small shelters of Apollo. They were laboratory complexes with dedicated areas for geology, biology, astronomy, materials science, and medical research. Power requirements ranged from 25 to 50 kilowatts, depending on the configuration and crew size. Some designs called for multiple reactors, providing redundancy and allowing maintenance on one unit, while others continued operation. The reactors would be buried in the regolith, both for radiation shielding and thermal management, with only power cables running to the habitat modules. This is where the story takes its dark turn. Because while NASA engineers were calculating power budgets and habitat volumes, while contractors were designing reactor mounting systems and radiation shields, while the agency was committing these plans to paper and presenting them to Congress, they were missing critical information. Information that existed, that had been measured and characterized in extensive testing programs, but information they could not access because of classification barriers erected by the Atomic Energy Commission and the Department of Defense. The problem was not that space reactor technology was classified. NASA had clearances. The agency worked closely with the AEC on nuclear propulsion studies, on reactor designs, on the basic physics and engineering. The problem was more subtle and more damaging. The detailed hazard data, the precise measurements of radiation release during accident scenarios, the contamination studies showing exactly what would happen if a reactor failed during launch or landing. This information existed in classified test reports that NASA was not permitted to see. Understand what this meant in practical terms. NASA engineers needed to know how much shielding to place between a reactor and the crew habitat. This is not a simple calculation. It depends on the reactor design, the fuel type, the power level, the geometry of the installation, and critically, on what happens when things go wrong. A reactor operating normally produces a known radiation field that can be shielded with understood amounts of material. But a reactor that has experienced a coolant leak or a control failure or physical damage during landing, that reactor might produce very different radiation signatures. It might release volatile fission products. It might experience localized power excursions. The shielding requirements could change dramatically. The AEC had conducted extensive testing on these failure modes. They had deliberately destroyed test reactors under controlled conditions to measure what happened. They had characterized the release of cesium-137, strontium-90, iodine-131, all the nasty fission products that make reactor accidents dangerous. They had measured gamma-ray spectra, neutron fluxes, contamination patterns. This data existed. It sat in file cabinets at Los Alamos, at Sandia, at the National Reactor Testing Station in Idaho. But it was classified, not because of the reactor designs themselves, but because the failure mode analysis revealed information about nuclear weapons effects. The connection was not obvious, but it was real. Understanding how fission products disperse from a damaged reactor core requires understanding blast physics, thermal effects, and radioactive transport mechanisms that are identical to the physics of nuclear weapons fallout. The models used to predict contamination from a reactor accident were derived from weapons test data. The measurement techniques, the instrumentation, the analysis methods, all of this technology had dual-use implications. So it was classified, buried behind security barriers that prevented NASA engineers from accessing it, even though they had legitimate need and appropriate clearances. This created an impossible situation. NASA was planning to place nuclear reactors on the moon, devices that would be launched on rockets, landed on an airless body with 1/6 Earth's gravity, operated remotely or in close proximity to crew, and potentially abandoned in place when missions ended. Every one of these operations carried risk. A launch failure could scatter reactor fuel across the Atlantic. A landing accident could breach the reactor vessel and contaminate the landing site. A coolant failure during operations could expose the crew to radiation. An abandoned reactor could become a hazard for future missions to the same region. NASA needed to quantify these risks, to design mitigation measures, to prove to Congress and the public that the benefits justified the dangers. But they could not do this properly without the hazard data. They could make conservative assumptions, and they did. They could use unclassified reactor physics codes to estimate radiation fields, and they did. They could design shielding based on worst-case scenarios, and they did. But they could not perform the detailed safety analysis that the mission actually required. They could not tell Congress with confidence how deep to bury the reactor because they did not have access to the contamination dispersion models. They could not specify crew shielding mass with precision because they did not know the exact spectrum of radiation that would emerge from various failure scenarios. They could not plan emergency procedures because they did not understand the timeline of a reactor accident in lunar conditions. The burial depth question was particularly vexing. Lunar regolith provides excellent radiation shielding. It is effectively rock powder, dense and uniform, and a few meters of it will stop most radiation. But how much was needed? The answer depended on the reactor design, the power level, and critically, on whether the reactor was operating normally or had experienced some failure. An operating reactor might need 2 meters of overburden. A damaged reactor leaking fission products might need 5 meters or 10, or might contaminate the regolith so thoroughly that burial was pointless. NASA did not know because the AEC would not share the data. The contamination studies were equally problematic. The moon has no atmosphere, no weather, no rain to wash away contamination. Radioactive material released on the lunar surface would remain there, effectively forever, moved only by micrometeorite impacts and the slow gardening effect of cosmic ray bombardment. A reactor accident could render a large area unusable for future missions. But how large? What isotopes would be present? How would they distribute in the regolith? What radiation levels would persist after a year, a decade, a century? The AEC had studied these questions in the context of nuclear weapons effects on Earth. The models existed. The data existed. NASA could not see it. By 1966, the LISA program was running into serious trouble. The technical challenges were mounting, the costs were escalating, and the safety questions remained unanswered. NASA tried to work around the classification barriers. They commissioned their own studies using unclassified data. They hired contractors with appropriate clearances to perform analyses using classified information and deliver sanitized results. They negotiated with the AEC for access to specific data sets. None of this worked well. The unclassified studies were too conservative, predicting shielding requirements so large that the reactor systems became impractical. The contractor studies delivered conclusions without the supporting data, making it impossible for NASA engineers to verify the results or adapt them to design changes. The AEC negotiations moved slowly, bogged down in bureaucratic processes, and genuine security concerns. The political environment was shifting as well. The Apollo program was consuming enormous resources. The Vietnam War was escalating, draining federal budgets and public attention. The initial enthusiasm for space exploration was fading as the reality of costs became clear. Congress was asking harder questions about NASA's long-range plans. The moon-based concepts, with their nuclear reactors and extended missions and multi-launch architectures, looked expensive and risky. Without solid safety data, NASA could not make a convincing case that the risks were manageable. MOLAB died quietly in 1967. The program was not canceled in any dramatic fashion. It simply faded from planning documents, replaced by more modest concepts that did not require nuclear power. The lunar roving vehicle that eventually flew was battery-powered, limited to a few kilometers range, operated only during the lunar day. It was a useful vehicle, but nothing like the mobile laboratory that had been envisioned. The LISA program lingered a bit longer, gradually shrinking in scope until it too disappeared, absorbed into the general post-Apollo planning that never quite materialized into hardware. The SNAP reactor program continued, but without a clear mission. SNAP 10A remained the only U.S. reactor to operate in space. More advanced designs were tested on the ground, but never flew. The AEC built and tested SNAP 8, a 35-kilowatt reactor intended for space applications, but no spacecraft ever used it. The technology worked, the engineering was sound, but without NASA missions to fly them, the reactors had no purpose. By the early 1970s, the space reactor program was essentially dead, kept alive at minimal funding levels as a hedge against future needs that never arrived. The Soviet Union faced similar challenges but responded differently. They flew dozens of nuclear reactors in space, primarily for radar reconnaissance satellites that needed more power than solar panels could provide in low Earth orbit. The RORSAT program operated from 1967 to 1988, launching 33 reactor-powered satellites. Several failed, including Cosmos 954, which crashed in northern Canada in 1978, scattering radioactive debris across hundreds of kilometers. The Soviets never attempted a lunar reactor, but they demonstrated that space nuclear power was technically feasible if you were willing to accept the risks. The classification barrier that hampered NASA in the 1960s was not unique to that era. It reflects a fundamental tension in nuclear technology development. Information about nuclear systems is inherently dual use. The physics of reactor safety overlaps with the physics of weapons effects. The engineering of radiation shielding applies equally to protecting spacecraft crews and hardening military systems against nuclear attack. The contamination models that predict fallout from a reactor accident derive from weapons test data. This creates situations where civilian agencies need information that exists in classified military programs but cannot access it without compromising security. The problem persists today. Current plans for lunar bases and Mars missions include nuclear power systems. NASA is developing the Kilopower reactor, a small fission system designed to provide 10 kilowatts for surface operations. The technical challenges are similar to those faced by LISA planners in the 1960s. The safety questions are the same. And while the classification environment has changed somewhat, barriers still exist. Some information remains restricted. Some analysis tools are not available to civilian engineers. The lessons of the 1960s have been partially learned, but the underlying tensions remain. What makes this story particularly frustrating is the waste. The technology existed. The engineering was sound. NASA had capable engineers and adequate budgets, at least initially. The AEC had the safety data. The information was there, sitting in file cabinets, unavailable because of security classifications that may or may not have been necessary. We will never know if the LISA program would have succeeded if NASA had full access to the hazard data. Perhaps the safety challenges would have proven insurmountable anyway. Perhaps the costs would have killed the program regardless. But we do know that the classification barriers prevented a proper attempt. They forced NASA to plan in ignorance, to make decisions without adequate information, and ultimately to abandon concepts that might have worked. The alternative history is tantalizing. Imagine MOLAB traversing the lunar highlands in 1972, its reactor humming quietly beneath the regolith, its crew exploring regions that remain unvisited to this day. Imagine a permanent base at the lunar South Pole, powered by multiple snap reactors, operating continuously through the long lunar night, supporting scientific research that could not be done any other way. Imagine the engineering knowledge gained from operating nuclear systems in space, the confidence built through successful missions, the foundation laid for more ambitious ventures to Mars and beyond. All of this was possible with 1960s technology. All of it was planned, at least in preliminary form. None of it happened, in part because the people who needed to know could not access what others had learned. This is not a story about technical failure. The reactors worked, the designs were viable. This is a story about institutional failure, about the ways that security classifications and bureaucratic boundaries can strangle innovation. It is a story about the cost of secrecy, measured not in dollars, but in lost opportunities and abandoned dreams. The nuclear moon base was not science fiction. It was engineering, solid and achievable, killed by information barriers that served no clear purpose and protected no vital secret. Today, the plans sit in archives. The LISA documents are declassified now, available to anyone who cares to request them. The MOLAB designs can be found in NASA technical reports from the 1960s. The SNAP reactor test data, at least some of it, has been released. You can read about the missions that were planned, the hardware that was designed, the future that was imagined and then discarded. The information is there, too late to matter, too late to save the programs it might have enabled. The reactors that could have powered lunar bases were tested and proven, then shelved when the missions disappeared. The mobile laboratories that could have explored the moon remain paper studies, occasionally rediscovered by new generations of engineers who briefly wonder why we gave up on such capable systems before flying them even once. The lesson, if there is one, is about the fragility of ambitious programs. They require not just technology and funding, but also information, access, and institutional cooperation. When any of these elements fails, the entire enterprise can collapse, leaving behind only documents and photographs and the lingering question of what might have been. The nuclear moon base was real, at least on paper. It could have been built. It could have worked. That it was not tells us something important about how we make decisions, how we handle information, and how easily we abandon difficult goals when obstacles appear. The moon is still there, still airless and cold, still waiting for the permanent human presence that was planned 6 decades ago. The reactors that could have powered that presence exist in museums now, or in storage, or were dismantled long ago. The knowledge remains, scattered and incomplete, a testament to the missions we chose not to fly and the future we decided not to build. If you enjoyed this story, hit subscribe for more stories where history, technology, and human ambition collide. Thanks for watching.